Okay, so what we're going to do is we're going to do this exercise kind of like we did the proton one last time, but we're going to do it for carbon 13. Remember, proton, we had 4 things we looked for, which was number of peaks, shift, intensity or integration, and peak splitting. Okay, we don't have that in carbon NMR. All we have is position and number of peaks. So we have to identify our unique carbons, and that'll give us our number of signals. So we're going to do that here. And I need to turn the display on so everybody can see. There we go. Turn this off. HDMI. There we go. And there we go. Nope, I need to reshare. Okay. Stop share and then reshare. Okay, there it comes. All right, there we are. So anybody else not have one? All right, so here we only have to predict shift and our number of peaks. So again, we're going to look for unique carbons, but don't forget, when we were doing proton, you could skip carbonyls. You can't skip carbonyls in carbon NMR, okay? So in this case here, if we were to predict the number of hydrogen peaks it would have 3 hydrogen peaks because it has 3 different types of hydrogen. But here in our carbon, we have 1, 2, 3, 4. Okay, that carbonyl counts. So we should get 4 peaks right here. And I'm going to label them A, B, C, D. Okay, which one's going to be furthest downfield? The carbonyl, right? It's B. That's going to be all 200 because it's a ketone, right? So we're going to have 200 over here and 0 over here. And so we're going to have 1 peak there at the 200 for the ketone. And then these A and C are going to be further downfield than D. Why? Because they're closer to the oxygen, right? And so we're going to have A and C probably around 50 or so, A and C. And probably C is going to be a little closer to 0 because it has that the carbon on the other side that can donate electronegativity. A doesn't have that. So that's going to be there. And then, of course, our closest to 0 is going to be the D, probably somewhere around 15 or 20. Okay. So we were able to, just by looking at our thing, get a really rough idea about what our, and then this is our TMS, our standard, so that you know where it is. Okay, so now we can do that again. Let's do this for this one. Remember right here, we had 1, 2, 3, 4, 5 different signals for hydrogen right here, but we only have 4 signals for carbon, okay? We're gonna have A, B, C, and D. And which one's gonna be most downfield? B, because it's attached to the oxygen. So we're gonna have B, it's gonna be somewhere around 60. And then 0 is down over here, 0 over here. And then we'll have, of course, A and C are going to be pretty close to each other, but upfield from B. And so we have C and A over here. And then again, D is going to be the closest one to 0. It's going to be most upfield because it's the furthest away from that oxygen.
Talk on this one, the A is
yeah, no, they're together. They're probably going to be right next to each other, and the C is probably going to be a little lower. So I'll just switch them here. So A and C. There we go. That'll make it clearer. So we were able to get that. And so when we look at our next exercise, which is the back of this page here, we'll start looking for number of peaks and then those general ideas of where the shifts are. Okay, so, all right. let's do this one right here. Trying to mute my watch here. Okay, so this is going to be A, B, C, and D. And which one's going to be most downfield? D, because it's bonded directly to the oxygen. What's going to be next most downfield? Probably C. And so we're going to have one for D here. It's probably going to be up around 60 to 75. That's going to be D. And then C is going to be below that because it's got an oxygen bonded to it. Then A is going to be next because it's next to the bromine. And then last is going to be B, but it's not going to be that close to zero as the other ones were. But we have 4 peaks that are all going to show up probably between 25 and 60 ppm because of that. Okay. All right, so let's do the next one. Okay. Yes.
So is the sorry, can you just go real quick?
Oh.
So is C further downfield from A because oxygen is more electronegative than bromine?
Yes.
So
Yeah, and if you look at where the shifts are for those, the bromines are bromine and the halogens are just below oxygen. Oxygen is more. And if you look where oxygen is, you know, it's like almost next to fluorine.
Yeah.
And then the electronegativity goes down as you go down a column. So
would nitrogen be more so than the halides?
It doesn't shift it as high because it's not as electronegative. So what you'll see is that they kind of, if you look at the table, usually amines are just below, nitrogen containing compounds are just below the oxygen containing compounds. And right there where they actually kind of, the halogens are right next to where the amine is as well. All right, so now let's do this one right here. We have 6 carbon signals, right? No. I think that this right here and this right here are going to give us one signal. They look the same, right? They have the same connections. And then we're going to have this right here is different than any of the other carbons because it has 2 carbonyls attached to it. That's going to tell us something about its shift too. Okay, now we have these 2 carbons look pretty much alike. They're each attached to a carbonyl on one side and a CH2 on the other, which brings us our last one here. So we actually have 4 peaks. 4 peaks. Even though there are 6 carbons in the structure, we have symmetry, and that gives us 4 peaks. And so if we were going to do that, so let's label this one, I guess we'll label this one A, B, C, and D right here. Which peak is going to be furthest downfield? C, correct. And it's going to be right at 200, 200, and that's C right there because of the carbonyls. Okay. Then which one's going to be next? A? Wouldn't it be D because it's in between the 2 carbonyls?
I wrote the letter back.
Oh, okay. It's D because it's there. And so it's because it's not a carbonyl, it just has the influence of the 2 carbonyls. It'll probably be way down here at around 50. Okay. And then the next one is going to be, let's see, that's D. D. So what's going to be next? B or A? B, because it's right next to the carbonyl. And so it's going to be a little bit here, probably around 40. And that's B. And then A is going to be almost down around 0. Okay. So we can recognize that pattern from where we have it. Okay. So now let's apply what we just learned here to this structure here. Okay. So I have a thing here. So this is 100, this is 150, this is 200, this is 50, and this is 0 here. Okay. So what does that tell us right now we have? You know, what's the first downfield peak we have? That downfield peak. It's between 150 and 200. So it's not a ketone or an aldehyde. it has to be a carbonyl with an electronegative atom attached to it. So it has to be an ester, an amide, or a carboxylic acid. Okay, so, well, that kind of answers our question now. Which of these compounds is a carboxylic acid? Okay, well, it's this one right here. So it's probably this, but let's predict how many peaks that one would have. Yes.
I don't have that.
Oh, you don't have that page?
I have
Okay. You should have gotten 2 sheets.
this. I think this one's proton.
Oh, this is the second sheet. Yeah, this is.
Oh, I should have gotten
that's- You should have got 2.
Oh, no,
It's a
that,
rack.
sorry.
Okay. So let's double check and make sure, let's predict. Okay, so we're gonna have 1 carbon peak, 2 carbon peaks, 3 carbon peaks, 4 carbon peaks, 5 carbon peaks. The carbonyl is probably this one right here. And this is probably, let's see, 1, 2, 3, 4, 1, 2, 3, 4 in that order. Okay. So just knowing that this wasn't up here, it couldn't be a ketone or an aldehyde, which gives you, or eliminates 3 of your different choices here. Now, what if we had it and then we added IR to this? You'd have a big, huge hump going all the way across the 3000 mark for the hydrogen bonding of there. And for Proton Nmr, we're going to have triplet right here. And then we have 4. So 4 is 5. So this would be a pentet. You have 1, 2, 3, 4, 5. So this would be a sextet. This would be a triplet. So we could actually identify it that way as well. Okay, questions on that? Okay, so look for your number of peaks and the shifts. Have those shifts familiar enough that you'll know that, oh, you know, things with oxygen mono are here, and then alkenes are here, and benzene rings are here, and then these are carboxylic acids, and then aldehydes and ketones are here. Have that, you know where those different ranges are. Not the exact number, just the range. Okay, so now we have a new one. And again, we have our 150 and 200 here. So it's between 150 and 250. So that means we have a carboxylic acid or an ester or something. We have a carbonyl, but it's not an aldehyde or a ketone. Okay, and we also have a peak here between 100 and 150. What's that? It's probably an alkene. Exactly, it's an alkene. And then we have something above 50. So that's probably something bonded to an oxygen. And then we have our last peak here, way down at the end, probably farthest away from an oxygen there. So now we have 3 distinct things to look for. We're looking for a carbonyl with an oxygen or a nitrogen attached to it. We don't have nitrogen in our choices, so that's all. So from just this peak right here, we can say it can't be this one. Our carbonyl is not high enough. It's not over 200. So it can't be that. Okay. So the other 3 structures look like they can go. So let's see. This would have 1, 2, 3 peaks because it's symmetrical, right? So can it be that? No, because we have 4 peaks in our spectrum. So it can't be that one. Okay. So now the last 2, they each have 4 spectrum. They each have 4 signals. They each have a carbonyl that's bonded to an oxygen. But which one's going to determine it? The alkene peak. It's above 100, so it can't be an alkane. So it has to be the alkene. So it has to be this one. Okay. So that means it must be this one because this one doesn't have an alkene.
Real quick, how come you said the first one was an option?
Because there is no electronegative atom attached to the carbonyl. That carbonyl would be above 200. And our carbonyl is just above 150. So it's about 160, 165. So it can't be an aldehyde or a ketone. It must be a carboxylic acid or a carboxylic acid derivative. Okay. So just knowing that this area here is giving you your alkene, and then this is something attached to an oxygen, and then this is something that's only attached to carbons or something. Now you can look back at the structure and say, oh, the alkene, the carboxylic, the carbonyl with an oxygen on it, and then there's a a carbon bonded to an oxygen directly here, like an ether or an alcohol. So we can see each of those structures, each of those features in here. All right, questions on that? Okay, so that is kind of how I would like to ask questions on the quiz and final exam. So look for that kind of stuff in there. Let's see, Nmr Activities, this is the next one. Now, the other thing you can do is, if you're not sure, you can compare the Proton Nmr to the Carbon Nmr and say, oh, for sure, it's got to be exactly this. Okay, so we have some choices here. We have an ether, an alcohol, a carbonyl, and another alcohol right there. And let's look at the Proton Nmr first. Okay. Okay. So it has like, okay, this looks like a doublet. This looks like a triplet. This looks like it's 1, 2, 3, 4, 5. It's either 5 or 7. Can't tell right there. Ooh, what's that weird thing right here? What's that? Does NMR usually give a broad peak? No, it only gives a broad peak in one instance, when there's hydrogen bonding. Okay, so this is probably an OH because it can hydrogen bond. Okay, so we have that. And so we have probably something that has a whole bunch of hydrogens nearby. And then it looks like this one's probably bonded to the oxygen itself. And this one's probably bonded to this one because of this, the pattern there. But we'll see. Let's see. All right, now let's go look at the carbon NMR and see what we get. We have a total of 1, 2, 3 signals. 3 signals, okay? And the highest one is right here at what this is 50, 60, 70. So do we have a carbonyl? No, no carbonyl right here. So now let's look at our choices again. One of our choices is a carbonyl. Can't be that one because there's no carbonyl in the carbon NMR. Okay, it can't be this one. Why? It would have 3 signals, and it would have 3 signals in the proton NMR too, because there is no acidic hydrogen. How many signals do we have in our proton NMR? We have 4. So that can't be it because there would only be 3 signals and no OH group. So that gives us a good thing saying, okay, so now we have a choice here. Let's see. How many would this give us? This would give us 1, 2, 3 in the carbon signal. Okay. This would give us 1, 2, and then look, these 2 are equal right here. So that would probably give us 3 signals in carbon NMR. Okay. So how are we going to tell them apart? Well, let's figure out what our splittings would be, right? So on this one right here, this doesn't split, right? So we would have a single peak there. This has a total of 1, 2 adjacent protons nearby. So this one right here is going to be a triplet. And it's going to be the furthest downfield because it's bonded to the oxygen, right? Okay, so there's a proton here. So that's a triplet, and then 1, 2. So we have 2 there. So now let's do this one right here. It has 1, 2, 3 plus 1. So there's 3 as our N. So we'd have a quartet right here. And then these over here would have 1, 2 equivalents. So that's 2 is our N. So N plus 1 is equal to 3. So this would be a triplet. So we would have a triplet, quartet, triplet for that compound. Okay, let's see what we'd have here. We'd have right here, we have 2 protons and they're going to be split once because there's only 1 proton here. So that's going to be a doublet. We have these 6 protons that are all the same next to 1 hydrogen here. So that's going to be split into a doublet. And then we have this right here that is going to be split by 6, 7, 8. So it's going to be 8 is our N. So it's going to be 9. So 9 right here. So now let's look at this, our proton NMR. Looks like we have like a triplet, a doublet, and I don't know, that could be 9. Can't tell. Okay, now, does that convince you which one it is now? Can it be this one? No, it doesn't have the right splitting. We looked at our carbon NMR, made sure it had the right peaks, and they're in the right place. But to choose between the two, we had to go to our peak to peak split in the proton NMR. So the correct answer is this alcohol right here. Okay, questions on that? See how you put the paper pieces together. Don't just freak out and say, I don't know. Just, what do I know? I know this. It should have this many peaks. Go backwards if you have to, but it will, it will let you figure out what it is by that. So let's do the next one, the one on the back of the page here. And so we have something right here. This is a triplet. Here, I'm going to blow this up, make sure. Oh, no, it's not. It's a quartet. So that's probably a quartet then. Maybe. And then that one looks like a single. And that one looks like a triplet. Okay. So this is one of those classical patterns, a 4 and a 3. And notice where this 4 is. It's next to an oxygen. So I'm going to say we're going to have something that looks like this as a fragment in our system. And this element right here is the one that's going to give us this 3-4, because this is next to 3 hydrogens, giving us a quartet. This is next to 2 hydrogens, giving us the triplet. Okay, so we're looking for at least one fragment in our system. Okay, all right, let's see how many things we have at the end here. We have 1, 2, 3, 4 carbon peaks. This right here is the solvent right here, and it's 3 little peaks together, and so that's how we know it's a solvent. Anyway, so let's see. So we have that. Oh, and we have something up here. So this again has to be a carbonyl next to an electronegative atom like oxygen. This is probably a carbon bonded to an oxygen, and these two are probably far away from it. Okay, so those are the evidence we have. So let's take a look here. Can it be this one? No, the carbonyl is not high enough. If it was above, almost 200 or around there, we could say yes. Okay, so it can't be that one. Can it be this one? No, because we didn't see it in the proton NMR. We didn't see the hydrogen in the proton NMR. So it can't be that. So it's got to be one of these other things, right? Now, according to what we were looking for in our proton NMR, it looks like we have an oxygen bound to an ethyl group here because of this and the peak-to-peak splitting. 2 things are telling us that it has this fragment in it. So let's go look at our choices here. We have one where it would be bonded directly to the carbonyl, and that peak would be down here between 2 and 3. So that doesn't support our data. So that means this can't be it either. So that means this must be it. Okay, now let's double check. We're going to get a quartet here. We're going to get a triplet here. We're going to get a singlet here in our proton NMR. And we're going to have 1, 2, 3, 4 peaks in our carbon NMR. We have 4 peaks in our carbon NMR, and our carbonyl is in the right place. And we have 3 peaks in our proton NMR, and we have the right splitting. So it must be the right answer. Okay? So if you have to predict, go backwards, predict where they should be. And then you should be able to identify from the graph the pluses and minuses. That supports your premise. Questions on that? Okay. Does this make carbon NMR more understandable now? Okay. Look for those number of peaks. Don't forget your carbonyl. All right. So now let's go back to the chapter. And I think it's this one. Oh, I uploaded a new one. Yeah, shorter version. Yeah. So So we're going to start with, and we're going to finish up mass spec today. Okay. Now, mass spec is really good because number one, it tells you the molecular weight of your peak, of your molecule. So you can actually start doing empirical formulas and trying to figure it out. We're not going to do that. We're going to just go on to looking at the good things you can find in mass spec. So molecular ion peak is the highest peak, the highest molecular weight peak, and it always has a little bit of an isotope in there. And I'll show you another slide on that. Then the next most important thing is our base peak, being able to identify your base peak. Your base peak is the biggest peak and is going to be the one that is the most stable fragment because it's the most abundant we found. The relative abundance of each thing. So when you look at your different peaks, they're all scaled to that base peak. The base peak is always 100 and everything else is a percentage of that base peak. So it's going to be smaller. Okay, and then fragmentation pattern. You can see an OH clip off because that'll lose 17. You can see a CH3 clip off because it'll lose 15. You can see a CH2 fall off because it'll lose 14. You'll see these things falling off and there's their fragmentation pattern. Okay, so you should be able to identify those four things on any spectrum here. So obviously this is our molecular ion peak because it's the highest one up. And this is our most stable fragment right here. And we get that most stable fragment from breaking either here or here to give you 3 carbons is our most stable fragment. Okay. And then what can happen there is with your most stable fragment, it can then decompose again to give us another fragment right here. Why does it do this? We have a primary carbocation right here. By losing 2 hydrogens, it can create an allylic carbocation. And an allylic carbocation is more stable than a tertiary carbocation. So that makes it the most stable fragment. And that's why we're going to see a bunch of it show up in our system. Okay. But let's talk a little bit about isotopes now. I said that the first time I introduced that molecular peak, I said, look at there's a little teeny peak right next to it. It's about 1.1%. 1.1%, 1 mass unit higher, M+1, the molecular weight +1. So that is the carbon 13 we see in our system, naturally abundant about 1.1%. And so we'll see for this carbon is going to give us our normal peak at 12, but then we're going to have 1% of it at 1.1. Okay, so and so that's an M+1 peak. Okay, because it's only 1 mass unit higher. Now we can also do that for hydrogen and deuterium. It's not really abundant enough to make it show up in our mass spec usually, but we can see it. There's a little teeny peak for nitrogen as well, but there's actually a little peak for oxygen +2. Oxygen +1 would be oxygen 17. It's really small, but the one you can actually see sometimes is oxygen +2. So there's 2 extra neutrons, making it oxygen 18. So that's an M molecular weight +2 peak. Okay. Silicon, fluorine only has the 1 isotope, so you don't have to worry about that. Silicon actually has a lot of them, including 2 that are significant. Its M+1 is 5%. And its M+2 is 3.4 or 3.35%. So you can actually see those on the mass spec. They're big enough to see. If we can see that 1.1, you can definitely see the 5 and 3 here. Phosphorus only has the 1 isotope. Sulfur has a little bit of a +1 and a lot of a +2. So that M+2 for sulfur shows up as about 4%, which is easily noticeable. But the next 3 right here are the ones that are the most important. They're the halogens. Chlorine has an isotope, a +2 isotope that is 32% based on the, would be a 32% of the base height for the chlorine 35. Okay, so what you're going to see is you're going to see an M+2 peak, but it's going to have a specific pattern. It's going to look a certain way. And I'll show that on the next slide. Bromine is similar, but it's got a M+2 peak that's about half of all of your bromine. So half of it is your 79, half of it is your 81. So you're going to have two peaks that are going to be an M+2 apart, and they're going to be about the same height. Okay, and then iodine, this is its primary isotope, and so we only see iodine by itself. Okay, so let's look at what those peaks look like when we have things like chlorine and or bromine in here. So let's look at this one right here. Okay, so we have an M and an M+2 peak. And the M+2 peak is 1/3 of the height. Oh, there we go. 1/3 of the height of this main peak. This is the pattern to look for chlorine. Okay, if it's 1/3 the height of the peak, and notice this one, it does it here too. That means whatever fragment this is, it still has the chlorine on it. Okay, so let's look at bromine then. In the case of bromine, we're going to see two that are almost the same height, an M and an M+2. So it's 79 and 81 on their masses there, and they're equal in height. So you can tell the difference between something with chlorine in it or something with bromine in it just looking for these two patterns. Okay, doesn't work with fluorine or iodide because that does. But also look at this fragmentation pattern. Okay, so the thing that fell off first is the bromine, because our fragment down here does not have that same pattern. And so our bromine fell off first. And so the rest of it is the rest of our material. And it's 43, which means there's 3 carbons in it by molecular weight. And so we can do that. All right, questions on that? So let's see. Isotopes, yeah, okay. So this is really important here. So the last thing is actually called the nitrogen rule. It's pretty cool. It turns out most of the time when you do a mass spec, you're going to get an odd number, okay? Now, if you end up with an even number, chances are you have 1, 3, or 5, an odd number of nitrogens in there. Because nitrogen has, its primary is 14, but it has another proton on it because it bonds 3 times. And so it ends up with an odd number if you have an odd number of nitrogen. So if you have 1 nitrogen, it's going to be odd. 3 nitrogens. If you have 2 nitrogens in it, guess what? It goes back to even. Because those two, adding the 2 odds together cancels it out. So when we look for things like that, if you're given a little mass spec like this, and you're saying, oh, my parent peak is at 73, and you're given 3 choices of what the compound could be, because it's an odd number, you're going to choose the one with nitrogen in it, because odd numbers give us our nitrogen in our system. Okay, questions on that? Okay, so in mass spec, well, we're not going to use too much of it, but it will be on the final. So go to the ACS study guide and figure out how they are the stuff that they want to ask for that. I'm pretty sure it's the same stuff I'm going to ask for it, but I'm not sure. So we'll see that. Okay. So the last thing we're going to talk about is we're going to send this is just for information, how we can use this in the lab. And most of the time, mass spec is really good because, if you have a pure compound, you can get its molecular weight and you can get its fragmentation pattern, and then you can use the computer and say, hey, does this compare to anything in my library? Okay, that's great if you have a pure material, but what if you have a mixture of things? Well, if you have a mixture of things, what you want to do is you want to separate them first before getting that. And so the most common way we're going to do that is what we call GCMS, gas chromatography mass spec. And so the gas chromatography here, this is where it separates your compounds. And so what you'll have is that you'll have the first thing come out and go through the mass spec, and then you'll get its mass. So the second thing comes out, you'll go through the mass spec, you get its mass. And so you can actually get the mass of each and every component in a mixture if you use the gas chromatography to separate them into different compounds first. Okay, so that is the last of chapter 9. Questions? Yeah.
Just for the gas converter, how does it read like the like separate?
Oh, so what, how does it do it? Well, so here's, well, your compound comes over here, it's already volatile. It gets hit with an electron beam, turns it into a radical cations, right? Those radical cations can fragment, right? But we don't see the radicals, we want to see the positive charge. So what we do is we have these two things right here, those are magnets. And what they're going to do is they by tuning the magnet, it can attract the positive charge to one side or the other. And so it can focus it in where the detector is. And then by the time it takes it to fly, and the amount that it was moved by the magnets here, you can detect its mass. But that's why that positive charge is so important. And that's why we don't see the radicals, we only see the positive charges. Okay. All right, good question though. I forgot to say that. All right, so now we're going to switch gears a little bit. We're going to go to, oh, this is the wrong class. We're going to go to this one and chapter 10. But first, we're going to take roll. There we go. Seeing some more new faces in the yard. Hi, I'm your professor, Dr. Yes. Yes. I should be right here. Yep, I am recording. I didn't record my afternoon class the other day, and so they had to watch this one. So, but they'll usually I'll post both, and so it's easy to find. Okay, so we're going to switch gears a little bit. In all our reactions and our reaction methods up to now, we've been moving pairs of electrons. Those pairs of electrons in the double bond reach out and make a new sigma bond. Those pairs of electrons are used on our nucleophiles. Those pairs of electrons, pairs of electrons, pairs of electrons. Now we're going to change it and go with what we call radicals, which are not paired electrons. So they're single electrons, which makes them incredibly active. Okay, so we have two ways to cleave a bond right now. The first one we used a lot in the elimination reaction, where we moved those two electrons and where they were pulling stuff off of the base. And we call that heterolytic cleavage, because one will get the positive charge, one will get the negative charge, and the bond is broken. Okay, so they're leaving with unequal amounts of electrons. But what if you have a nonpolar bond? Okay, or two things that aren't very electronegative? Then it's going to be difficult for one to say, well, I get all the electrons and you get none, to make it heterolytically cleave. So what it does is it cleaves homolytically the same. Both walk away with one electron of that sigma bond, and that gives you your product. Now notice we have two different arrows here. In heterolytic cleavage, we have two barbs to represent the two electrons. Okay. In homolytic cleavage, we have one barb representing one electron. So when you're using that, make sure that you're using the single barbs that ends up with both of the substituents having the same number of electrons from the bond that just broke. Okay, so again, two barbs give us an anion and a cation. One barb gives us two radicals. Okay, and so these are called radicals or free radicals. And because they are unpaired and they want to be paired, they want to fill that orbital, they are reactive species, and we typically call them reactive intermediates. Okay, so when we have one, we have two kinds of reactions that can happen. You'd think, well, just a radical and radical can couple. Yeah, that's one thing that can happen. But the other thing that can happen is that you can have that radical abstract a hydrogen from a carbon with hydrogens on it. Okay, and it's called hydrogen abstraction. Okay, when it does this, the radical right here is going to use one electron, so a single barb right here. The other electron stays on the thing behind it. So that means whatever our halogen was, it has now transferred that radical to a carbon. And now there's a carbon radical. And that carbon radical can do the same thing. It can abstract a hydrogen from something and go back to itself, or it can react in other ways. Okay. The other way it can do is it can add to a double bond. Okay, your double bond has 2 electrons in its pi in the p orbital. Okay, it's going to use one of those and rehybridize to give you a sigma bond on one side. So we get our sigma bond on one side, but then we leave a radical on the other carbon because it only had 1 electron in the pi cloud that it could take with it because the other one was used to make that new sigma bond. Okay, so, but notice in both of these reactions, it generates another radical. Okay, so whenever you start with a radical and you have a hydrogen abstraction or an addition across a double bond, you still get a radical. Okay, so that means it could be really, really cool and very fast reaction that if you made a radical, it'll just keep on making more radicals until everything's complete. Okay, so those are the 2 types of reactions you can get there. And let's talk about the structure of that, okay? We saw that a carbocation is an sp2 hybridized orbital with an empty p orbital. We saw that it turns out a radical is an sp3 hybridized orbital with a single electron in the p orbital. So it has that same shape. It's got the trigonal planar and it's got the radical above or below that plane, and it can be on, it's on both sides, you know, it goes back and forth right here. So what does that mean about our radical? Okay, that means it's going to have the same type of stability trends that carbocations have because it has that same structure and that p orbital, but now instead of being empty, it has an electron in it. The more substituted your substrate is, the more stable the radical is. Okay, so you're looking for 3 carbons on a carbon, giving you a tertiary carbon. Your tertiary radical is more stable than your secondary radical, and which is more stable than your primary. And the methyl is the least stable. However, they are not as the carbocations are. You can make methyl radicals and primary radicals. Their energy difference between the primary radical and the tertiary radical is not as big as it is with carbocations. So we can't make methyl carbocations or primary carbocations in solution. We can only make them in vapor phase, i.e. mass spec. But in the case of radicals, the difference is not too high and you can make all 4 of these. It's just the tertiary is going to be more stable than the secondary. Secondary is going to be more stable than the primary. All right, questions on that? So now we got to figure out how to play with these things. Now that we know they have the stability here, okay? So what would drive something to break apart homolytically? Well, there's a couple of things that we can look for there, and part of that is energy, and part of that is if it's a non-polar bond, it's going to break apart equally, okay? So let's look about this, and we're going to define this as our by that bond breaking enthalpy, the energy required to break this bond, okay? So our change in enthalpy of our compound is going to be equal to the sum of all the products, all the energy of the products, minus the sum of all of the products. I'm sorry, the sum of all of the reactants minus all of the products. And that should give you a number. And if it's a negative number, that means it's exothermic, it's giving away heat. And if it's giving away heat, that means it's probably driven, the reason you're driving that reaction is you're giving off heat, you're giving off energy, you've made a more stable product, okay? And so we can calculate that by looking at the simple reaction here. We have hydrogen, hydrogen, and fluorine, fluorine, okay? Okay, and when they react together, very violently, I might add, they create 2 equivalents of HF.
Why is it violent if these that last? Why is it violent if these that last electrons for a long time?
Well, the reaction between the hydrogen radicals and the fluorine radicals is exothermic because it makes a more stable bond. So if we look at the energy it takes to break apart these 2 hydrogens, it takes 436 kilojoules per mole to break those apart into 2 hydrogen radicals, okay? Now, if we do it the fluorine, it actually only takes 159. Why? Electronegativity. Imagine how it comes back to that all the time. Okay, so if we subtract our reactants from our product right here, we're going to end up getting a total of 545 kilojoules per mole out of the reaction. So it's going to be exothermic. So why do we do it? It's a driving force. The driving force is it's releasing energy. It's going to a more stable product. Okay. And so when we do the same thing with something like a hydrogen abstraction right here, we can see that if we do a hydrogen abstraction to give us a primary radical, it actually takes more energy than doing a hydrogen abstraction to give us a secondary carbocation. A secondary radical. But notice the difference, not that much. Okay. In carbocations, it's like 50, 60 kilojoules. Here, we're only looking at 10 kilojoules difference between the primary and the secondary radical. Okay. So that's why we can make those methyls and primaries and secondaries, because the energy difference is not that great. Okay. So how can we use these for fun, right? So first of all, we want to have a way to generate our radicals. So radicals are formed covalent bond, or radicals are formed from breaking a covalent bond with heat or light. Okay. So the feature you're looking for is you're looking for two of the same atoms, and you want to break the bond in between two same atoms. Why? They both have the same electronegativity, and so that when they break apart going homolytically, one would have to have a positive, wouldn't have to have the positive charge or the negative charge. But I'm sorry, by breaking heterolytically, two electronegative atoms are going to, one of them have to have a positive charge. So instead, it breaks apart, giving radicals on each of them, so they break away easily. And so one of the things we use to generate these things, and we call those radical initiators, is the weak oxygen-oxygen bond. So we have peroxides where we can take, you can make a peroxide by oxygenating an ether or oxygenating a carboxylic acid. And so peroxide means it has per meaning one extra peroxide. So it's going to have two oxygens. And that gives us a nice bond here. Breaking these bonds are very easy. Most of them, like anything over like 50 degrees, and it'll pop open and give us generating a radical. So why is it important to generate a radical? Well, remember, we have two kinds of reactions we can do. We can do hydrogen abstraction and give us a carbon radical. So this could generate a carbon radical after you've generated that much easier to make oxygen radical. Okay, so you're initiating with that. The other thing we can do here is it can add to a double bond, generating another radical. So you can generate a radical both of those ways, hydrogen abstraction or reacting with a double bond, to get us to a carbon radical. Then the carbon radical can do all those other reactions. Okay, so we're using that initiator because it's easy to make the oxygen radical. And then as soon as it reacts either with a hydrogen abstraction or a double bond, it generates the carbon radical, which then you can make bonds with. Okay, so in every radical reaction, you have 3 steps. Okay, so I said, there's only 5 things that happen in a mechanism. Okay, well, in radicals, there's 3 things that can happen. First thing you do is you initiate a radical, usually with an oxygen somewhere. Okay, that oxygen is going to react with the substrate, and that's what we call the propagation step. So we have the initiation step where we're making that oxygen radical. That oxygen radical then reacts with a carbon to generate a carbon radical. Now that you have a carbon radical, it can react with other carbons to make other carbon radicals, either by abstraction or addition to the double bond, right? And then that'll keep going and keep going and keep going until you run out of things to react with, run out of double bonds, run out of hydrogens to abstract, and then you have what we call the termination step. In the termination step, that's where you remove all of the radicals. So what that usually looks like is either it abstracts a hydrogen or 2 radicals combine to form a sigma bond. Okay, so those are ways to do it. So why is this, so different than our other mechanisms? Well, because of these 3 different stages. Okay, so in the case of this one right here, this is the halogenation of alkanes. You can't do it with other reactions because there's no, we could halogenate alkenes. We did do that, but we couldn't do alkanes. They just don't react that way. We have to use a radical mechanism to do that. All right, and because if we have an alkane, we can't do an addition reaction with the alkene, so we must be doing hydrogen abstraction to generate a radical. Okay, so what do? We can start with chlorine or bromine here. And notice we're going to make our radical with heat or light with the chlorine first. Why? It's going to be easier to do because, and they're two chlorines, and so they'll want to break apart homolytically. They'll want to break apart with the radicals. So you're actually going to generate two radicals in breaking apart that one molecule of chlorine. Okay, so now you've generated your chlorine radical, and the next thing it's going to do is it's going to abstract a hydrogen and generate a carbon radical right here and HCl. Okay, it can't add across a double bond. We don't have a double bond, so it has to do the hydrogen abstraction. Okay, well then the methyl radical can then go react with another thing of chlorine and generate a chlorine radical, which can then go back and abstract a hydrogen and generate a carbon radical, which then can go react with chlorine to that. So it's propagation check. It just keeps going and going and going. Okay, until you get down to the point where you have no more of your material to react with, or you run out of chlorine, or you cool the reaction down so it can't generate radicals. And then what happens is you have radical-radical coupling. Now, in the case of a chlorine finding another chlorine radical, is that a bad thing? No, because that's what we use to start the reaction. It'll just go back to reactant, so that's cool. If we go with the chlorine radical going with the methyl radical, is that a bad thing? No, that's the product we were looking for. So that's a good step, but it does remove the radicals. It terminates the radical. So those are termination steps. Now, the unhelpful one is the one where you have two methyl radicals combining together to extend your chain out. You wanted the chloride, the chlorinated product. You've now made a impurity. So this is the bad termination step, is where you have your carbon-carbon radicals terminate each other, and they end up with that termination step. Questions on the mechanism here? Always has 3 steps: initiation, propagation, and propagation can be a number of different things, and hopefully they're generating the product that you're looking for, which in this case is a halogenated hydrocarbon. And then your termination steps, where all your radicals go away. But it doesn't necessarily mean it's the end of the reaction, because we can just go back and heat that back up and start it again. All right, questions? Okay, so let's figure out if there's a regioselectivity. So if we have this compound here, we have butane, so it looks like we're going to do that radical abstraction and halogenation. We have chlorine, so we're going to chlorinate the material. So let's figure out what our product ratios are, okay? So statistically, there are 1, 2, 3, 4, 5, 6 hydrogens, and they're equivalent, right? They're both at the ends. They have 3 hydrogens on each of those, so there's 6 of those. And there's 4 of the secondary type hydrogens, right? So in theory, if there was no selectivity, 60% of the time it would go on the outside because it's 6 of the 10 hydrogens. And then 40% of the time it would go on the inside because it's 4 of the 10 hydrogens. Okay, does that make sense? So we should predict that we would get more of the primary and less of the secondary, but that's not what happens. You actually get more of the secondary. Okay. Why? Let's see, we generated a radical, that chlorine radical with the heat, or in this case, light. And its first step to do is to make a carbon radical is to do a hydrogen abstraction.
The stability, right? Be more stable.
It'll make the more stable secondary radical. So even though there's fewer of those hydrogens, it can abstract. There's enough of an energy difference, 10 kilojoules per mole, that it will preferentially go for the more stable radical. Okay, generating your secondary, in this case, radical, which generates your secondary chloride, which is the primary product Notice you still make some of the others. I mean, it's still a very, again, the energy difference is not that much, but there is a difference in their rate. So if we just held the primaries as 1, it's actually 3.8 times faster to generate our secondary radical, and it's 5 times faster to generate a tertiary radical. So that's going to control your product ratio. Okay. Yes.
Can radicals shift the way that carbocations can to become more stable?
No. Well, no, because once you do your radical abstraction, then you'd actually have to have a hydrogen radical move over, and that doesn't. No, they don't move around. Wherever you put your radical is where it stays. Okay. But again, it's faster to do a tertiary than a secondary, and it's faster to a secondary than a primary. So you can get your product ratio correct. Okay, questions on that? So what can we do when we have more than 1? We actually can predict by the reactivity ratio of a primary versus a secondary and predict what our products will be. Okay, because if our primary is 1, the relative rate of 1, and our secondary is 3.8 times faster, we should be able to predict our product ratios here. And so what we're looking for is, in this case here, in that same reaction, we have a total of 6 hydrogens that are going to make those primary radicals. And we have 4 hydrogens that can make that. And so let's talk about those primary radicals. Those primary radicals have a reactivity ratio of 1. Okay, so that means 6 chances with 6 different hydrogens times 1 is going to give you 0.6. Okay, it's going to give you 1.6 relative rate. Okay, now let's look at the other one. We have 4 hydrogens, but it goes 3.8 times faster. So if you take 4 and multiply it by 3.8, you get 15. Okay, so that means for every 6 reactions that happened on that primary, 15 have happened on the secondary. Okay, so a total of 6 plus 15 makes a total of 21 reactions happen. Okay, so we have 21 reactions. And if we took 6 divided by 20 and multiplied by 100, we'll get the percentage. And the percentage of that is 29%. And if we did that same thing with the 15 divided by 21 for the total number of reactions that happen, we get 71. And what do we see? We actually experimentally got 29 and 71, which is kind of tricky because we actually got the product ratio, helped us calculate out what those ratios, those relative rates were. So that relative rate was actually calculated by doing the reaction and figuring out what your product ratio is. But now that you know them, you can predict your product. Yes, question. Yeah, didn't you?
Yeah. Are we going to be given the reactivities?
Those are them.
So those
Those
are
3.
constants. They don't change.
Those change for hydrocarbons, straight chain hydrocarbons. So, okay, so now that was with chlorine. Bromine is even more selective about which one it's going to generate. Okay, the reactivity ratios for bromine are actually 1 to 82 to 1600. So that means bromine is more selective. Okay, but with those reactivity ratios, what it means is that if you do the reaction in chlorine right here, you're going to get more of the secondary than the primary, and so we're going to be at 71 to 29 right here. If we do that same reaction, and the only thing we do is we switched out bromine for chlorine and hit it with light, the product ratio is actually 98 to 2, where it's on the secondary, because of this reactivity ratio. So if you were trying to make a really nice reaction and you had an alkyl halide you wanted to substitute, and you know you're going to have this nice substitution reaction, would you rather chlorinate your substrate or brominate your substrate? If you want the secondary, you definitely want a bromate. If you want the primary, you actually want to do the chlorination and purify because you have to separate out. You only get 30%, but if you wanted the primary, you want chlorination. If you wanted the secondary, you want bromination. If you don't want to purify it, you want bromination. So 2%. All right, questions on that? Okay. So we do this with bromine and chlorine selectively because fluorine is actually very reactive, explosively reactive in these kind of reactions. So it's very hard to do. And iodine is actually endothermic. So we don't actually see iodine react with these radical reactions very much at all. So let's talk about that selectivity here. Okay. So this means the greater the reactivity, the less selective it is. It's just trying to dump that energy as fast as it can, and it'll take whatever it'll get. Secondary fine, primary fine, just go, 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 go. Okay, but bromine is less reactive, and so it can wait a while and say, oh, you know, I don't need to get that primary hydrogen abstraction. I'll wait till I can get that secondary because, you know, it just feels better. And so that's why there's that selectivity difference. I mean, like the 1 to 82. So for every 83 molecules, 82 of them are going to be the secondary. Only one of them is going to be that primary. Okay. So then when we have that selectivity difference there, we want to try to use bromine as much as we can because it gives us one thing, unless you have something that gives you a symmetrical product. Okay. So in this case here, if you have cyclohexane, chlorination is fine because you only have secondaries. You only have secondaries. There is no choice. So there's not going to be 29% of a primary. It's going to be all secondary. And therefore, that makes the chlorination of the cyclohexane a useful reaction. Okay. But again, chlorine is way too exothermic and iodine is way too endothermic. Okay. All right, questions on that? So radical reactions actually can be useful for making alkyl halides that we couldn't make otherwise. Now, how would you get an alkyl iodide now? Well, you use the radical reaction to make a chlorine, and then you swap them out using nucleophilic substitution. So that's how you could do that. Okay. Now, that was hydrogen abstraction. Hydrogen abstraction gives you a radical, and then that radical can terminate or halogenate using that radical hydrogen abstraction method. Let's do the other one. Let's add it across a double bond. Okay. Now we saw that when we had HBr and added across a double bond, it went to Markovnikov's, right? The hydrogen went to the more substituted, the more hydrogenated side, and the bromine went to the more substituted carbon. Okay. So, and that was really good. We got that Markovnikov. However, if you have, oh, what was those conditions, right? Didn't we have conditions? Oh, in the dark, cold, because you didn't want it to form a radical. You want to do the addition across there and not do the hydrogen abstraction. HBr, if you add a peroxide to it so that it creates radicals, so you get bromine radical and hydrogen radical, it actually changes the system to make it anti-Markovnikov's. The addition of HBr across a double bond is anti-Markovnikov's in the presence of a peroxide. Okay? Because we've changed the mechanism. It's no longer an addition across here. What you're going to do is you generate a radical on one of those two sites there, and which the hydrogen or the bromine, whichever one came in first, is going to generate that radical on one of those two sides. Okay. So when we want this, we have changed the nature of our bromine. We've turned our bromine into our electrophile. Not the hydrogen. The hydrogen was the electrophile but now with peroxide, it turns your bromine into the electrophile, and therefore it goes anti-Markovnikov's. Again, this only works with HBr because of its selectivity. It does not work with HI or HCl because they are both endothermic processes. So it only works with HBr. So if you see HBr in an alkene, look for a peroxide. If it's peroxide, it's anti-Markovnikov. If it doesn't have a peroxide, it's going to be Markovnikov. Okay, so let's figure out why. Let's look at all the different steps. So our first step is initiation. We have a peroxide in there. We have to generate our radical. Our radical then reacts with our HBr, turning it into a bromine radical. And that is our reactive species. Now our reactive species comes and looks at that double bond and says, hey, I want one of those electrons to make my sigma bond, leaving one of my electrons left. And look what it does. When it adds to the end of the chain, it creates a secondary radical. Now that secondary radical can do hydrogen abstraction from HBr and terminate that and give us back a bromine radical, which then can continue to go through the system. Okay, now what can happen then? So those are our propagation steps. So we had our initiation step, that creating of the oxygen radical that turned it into a bromine radical. Then we have the formation of our secondary carbocation, a secondary radical that does our work, getting our bromine on our number 1 carbon. And then it does hydrogen abstraction to terminate that product. And then of course, we can also have a bromine do a radical-radical coupling and give us a different product. This is going to give us a dibromo compound, which is not maybe what you're looking for, but you're going to have a little bit of it. And then you can have radical-radical coupling where 2 of these carbon radicals will form together to make a bigger chain. This is a side product as well. So neither one of those are really productive for us, but we see why it's anti-Markovnikov. You turned it into a bromine radical that it's going to add to the more substituted side, leaving the more stable radical that then has to do your hydrogen abstraction, giving you your hydrogen on your more substituted carbon and your bromine on your less substituted. Okay, questions? Okay, cool. All right, so that's really useful. So we can brominate a hydrocarbon. We can chlorinate a hydrocarbon. It's just not as selective. We can then add HBr across an alkene, both Markovnikov, no peroxides, and anti-Markovnikov with peroxides. So now we have another tool in our belt of creating different little substrates to use for as we move forward. Okay. And so basically, because the reaction ends up with a hydrogen on the more substituted side, it's called anti-Markovnikov's, right? Technically, however, Markovnikov's rule states that the electrophile adds to the carbon with the more hydrogens. In the case of HBr without peroxides, the hydrogen is the electrophile. Okay. In the case of the bromine radical, remember that bromine radical is coming to interact with the double bond. It is now the electrophile. So it technically is acting as an electrophile and is on the less substituted carbon. So it's technically not anti-Markovnikov, but if you want to remember it that way, just to say that but the reason is it technically follows Markovnikov's rule because the bromine is the electrophile in this case. Okay. So, all right. So that means we can do that same little substrate. Remember this little substrate? We used 3 different reagents. We've got 3 different alcohols. Got hydroboronation gave us a primary alcohol. Oxymercurization, demercurization gave us our secondary alcohol. And then water and acid, it rearranged because of a carbocation. Okay, if we do that same kind of stuff with HBr without peroxide, we're going to form our hydrogen here, which is going to give us a secondary carbocation. And then we're going to do a 1,2 hydride shift and get to our tertiary alkyl halide product. But if we wanted the primary, we turn our bromine into our electrophile by adding peroxides. We get addition of bromine on the primary carbon, hydride abstraction on the secondary carbon, so we get a primary alkyl halide. Same substrate, 2 different reactions, 2 different products. That's the cool thing about chemistry. All right, questions on that? Okay, so let's see. I think I will stop there. And the next quiz on Wednesday will be just spectroscopy, just chapter 9. Okay, we'll do radicals after we finish this chapter. We'll finish this chapter up on Wednesday.
How many chapters do we cover to the end?
11.
11.
So this is 10. We have one chapter after this, and that's alcohols and ethers. Yes, the third exam is before the final.
It's not like a lot of stuff to cover in the after exam.
No, we will finish all 11 chapters, and we have a review. Then you'll have your exam 3, which is on the last, focused on the last 4 chapters. Then the final, which is comprehensive all semester. Okay.
Do you think it'd be a good idea to start like studying?
Yes.
Or it's like this focus on-
I would definitely get the ACS study guide out and study what you don't understand really well right now, and then brush up on the stuff you do understand as you get there. So you spend more of your time on the stuff that's getting you in trouble and do that earlier. And then by the time you get to the end, so that, then it's like, oh yeah, I got to remember. Oh, don't forget the carbon has this, hybridization. So, save the easy stuff for toward the end. Do the hard stuff now.
Okay.
Okay. All right.
Officer is Thursday at 11?
Let's see. Thursdays at 11. All right. I'm going to go ahead and stop sharing. I do them in person, but if you want to do Zoom, I can do that too.